Okay, let's get this party started. This is an overly dramatic title, really. So it's developing a PowerShell classification model, and the reason it's kind of overly dramatic, my self-discovery is, it's kind of my first model, right? And so this is kind of the process I went through from start to finish, from kind of observing high-level features and kind of saying, hey, this might work, and going through that whole process, and then also the pitfalls and solutions we came up with along the way. So this kind of follows pretty well after Ram's talk with the PowerShell that he mentioned. So that's one of the references that I listed at the end. There was an academic paper they had at the fairly recently. So this has kind of been our process for the last 2 years. So who am I? I'm Derek Thomas. I'm an applied security researcher at eCentire. We do managed detection and response. I'm a Converge Detroit conference organizer. There's a couple of us around here, so we hold a security conference every year, and a Michigan security member. So I consider myself a security data enthusiast. My whole life has been involving logs. So you're probably saying to yourself, I've lived a really hard life, and that's probably true. But so if you work with logs your whole life, you got to be pretty good at doing analysis, or that's a tool that should be picked up. On Twitter, you can hit me up, DTOM, LinkedIn, email. If you want to contact me afterward, I'm always open. So I have a couple goals here. I figure the audience is made up of kind of data scientists and maybe security professionals. For data scientists, I think they would like to learn about this problem, the strategies for detection, maybe working with subject matter experts on how they see things and how they identify malicious activity in the processes they go through. Security professionals, this is a concrete ML use case. You see ML all the time. It's buzzwords. Someone said ML blockchain AI. It's like, what does that actually mean? Well, this is a concrete use case and how we've derived value from it. And I think everyone should start looking at detection a bit differently. A lot of security professionals are very focused on like atomic IOCs, very detailed observances and things like that. And I think that moving up a level to more generalized detections raises the bar for attackers. And everyone really just learned from my experiences. I think that if old Derek saw this presentation, I would have saved myself a lot of time. So this is our first version of the PowerShell project. This was from probably implemented about 2 years ago. In the process, I went developing a proof of concept, and that proof of concept was used to say, hey, this is valuable. We need to operationalize this, spend time and resources to implement our production model to do real-time PowerShell classification across our entire environment. And as we go through this, knowing that you're going to see some pitfalls, you're going to see some things that say, hey, that doesn't really work. So I'm going to cover at the end the pitfalls and solutions to those problems. So here's the agenda. We're really going to talk about, PowerShell, the problem, why it's important, how to get data, and properties of malicious code. And then the PowerShell classification in part 2. It's really just how I started and went through my machine learning process there. So this all really started back in 2016. So it was a while ago. It's kind of how I feel PowerShell's malicious use of PowerShell started to gain extreme popularity. And I kind of followed true with Ram's slides there in 2017, 2016. And this began with as it always does, a simple request from one of my clients to monitor and alert on malicious PowerShell activity. So, following that, it's like, whoa, what does that entail? What is malicious PowerShell activity? So being from the world of logs, SIMs, things like that, creating use cases, I created rules, created hundreds and hundreds of rules. Then I bypassed those rules. Then I created more rules. And then I'm thinking, this is insane. There's got to be a better way for this. So that's when we kind of clicked, and it just, hit us that, maybe a classification model, looking at the things that we as analysts look at, would be the way to go. And so this is that story. So we'll start off from the beginning. Like, what is PowerShell? It's a scripting language legitimately used for any administrative activity within your environment. So basically, administrators can do anything they want and automate it through PowerShell, which is awesome. It's super flexible. But it's also, for those same reasons, increasingly leveraged by our adversaries and pen testers. To compromise servers and workstations, and what we call living off the land. PowerShell is available in almost every organization and every workstation that your users are on. So living off the land is using legitimate tools to meet your adversary's objectives, right? So they have the tools available. They can do almost anything they want once they have access to a system. So we dubbed this project Blue Steel, and I'm going to talk about that later. Everyone either understands immediately or not. So we'll see who gets that reference, or maybe scared to say they do. This was born out of client requirements for effective detective malicious PowerShell. Okay. So why is it important? You might say, well, okay, Derek, you can detect this. Why is this important? Why should I do this? Well, it can be leveraged in every stage of the attack. If you look at the MITRE framework, they have one tactic reference for PowerShell, which is true. It's for code execution. But with code execution, you can perform any step within your kill chain and meet their objectives. So from recon all the way to exfiltration and command and control. It's appeared increasingly used by our adversaries. So, I'm basing my observations strictly off of, new exploit frameworks that are coming out. So we mentioned a few, PowerSploit, PS Attack. It seems like every day there's some new tools to fill a void of offensive capability. Just from going to conferences like this, I've seen an increase in PowerShell talks to say, hey, here's how easy it is to use PowerShell to do offensive activities and defensive ones as well. But I'm more concerned with the offensive. We observed phishing payloads to our customers significantly, so it's been on the rise over the last 2 years. And then increased use in penetration tests. So I think penetration testers often rely on PowerShell. And with the Microsoft implementation for logging and script block logging, it's going to become more difficult. And so I see this being less the case in the future, but right now it's being used drastically. So PowerShell is extremely flexible. It can be used it's a dual-use tool. It can you can hide in plain sight because you can achieve your objectives, steal creds, or add a user to the domain. One of the cool things and not cool things is it can execute encoded commands. So you can feed it a base 64 string of code, and it can execute that natively. So that makes it tough for me when I'm looking at logs and you see an base 64 blob of text. Is that good or is that bad? I don't know. At first, I thought, okay, this is always going to be bad. And in reality, across a large sample size, we see significant use for legitimate reasons. So we see things like Chocolatey or Ansible deploying or doing activities using encoded commands. So I don't really think that just identifying encoding commands really works. With PowerShell, you can obfuscate and execute code. I'm going to show some samples of this. Basically, you can slice and dice, replace, rearrange, compress, encrypt the data, and then execute that code in any way you see fit. And then also, you can use it for fileless attack techniques. We've seen this significantly in kind of advanced attackers. So execute code in memory, run a scheduled task, and pull the code out of maybe a registry entry or something along those lines. Okay, PowerShell is important to monitor. I hope we're all on the same page there. First, you got to get the data. Like any data science or use case creation, you got to have the data. So where does this data reside? PowerShell is very nuanced, so it's very difficult. Data resides in multiple places. Each place has different amounts of data associated with this. So it can be executed in memory, from the command line, from a script file. So each one logs differently. So one of the main places we use is a Windows security log. They list the command line straight from the security log. And those are easy to get. Usually, most organizations are collecting these already. You might have to check to see if you're enabled process monitoring. Oftentimes, this is enabled already in many organizations. Even better would be PowerShell script block log. So PowerShell in version, I think 4 or 5, enabled script block logging. What that means is that any code ever executed by PowerShell is logged in a file and available for analysis. But this is a different log channel than the security log. So sometimes it can be more difficult to get. Enabling script block logging is more difficult by far than enabling the audit settings. I'm going to show you a resource for that, but it's GPO settings. You got to have the correct Windows management framework. You got to have the correct .NET settings, and you may not be up to date in many organizations. We see mature organizations can easily implement this, and some it's more of a challenge. Sysmon events, if you're familiar with Sysmon, that's kind of I don't want to call it an EDR agent, but it does process, significant process monitoring on Windows machines. It's a sysinternals tool and very popular in the security community. This logs process execution and can be used for getting command lines. And then any EDR solution. If you're familiar with EDR solutions like CrowdStrike, Carbon Black, they're doing significant process monitoring. Oftentimes they have logs that can come out of that, or you can query them for logs and say, hey, show me all the PowerShell commands and command lines. So here's an example, and I'm going to kind of try to outline the nuance of collecting these logs. So from the command line, I'm executing this encoded command. So PowerShell.exe with encoded command and then just a blob of text. So that's what we would see if we're monitoring these logs. So that can be difficult. But in reality, this is just showing the PS version table. It's showing the version of PowerShell. And I'm going to show you what this log looks like in the actual log. So here's the Windows security log, 4688. You can see that at the bottom it shows the encoded command. What I'm really concerned here is the process command line at the very bottom. This is a newer feature in Microsoft. You have to enable this through GPO. And I suggest everyone does this. So there's so much more value, and it's easy to extract the command lines from this. I'll show you a reference for doing that in a bit. But it's important to note that you see basically exactly what was typed on the command line is what's showing up down there. So here's a Microsoft script block log, and you'll notice that in the script block log, you see the actual code that was executed. So that was the base64 encoded command right there that shows you the version. So this gives you, I mean, if you're not seeing this already, this gives you so much more value because you can see the decoded commands. So that's a step that you kind of can skip with your monitoring solution, identifying the encoded command and then decoding the base64 blob. This can be, this might seem easy, but it's difficult because PowerShell has aliases and it's very flexible with -e, -ec, -encoded command, etc. There's a lot of ways to do this. So this will show that encoded command, and really we use this for identifying legitimate uses of encoded command, because we'll see a ton of obfuscated commands that cannot be decoded automatically if we haven't seen it before. But those are we've never seen a legitimate use of that yet. So here's the references for enabling command line process auditing and enable script block logging. I definitely recommend that second link for PowerShell Loves the Blue Team. That's kind of what the blog post from Lee Holmes I think in 2015 kind of got me into really looking at PowerShell, thinking this is important, and really how Microsoft, some of the features that they were implementing. At that time it was a little bit difficult for many organizations to transition to script block logging and implementing some of these features, but now it should be much more doable. So we enabled and we're collecting logs on the workstation or server. How do we get them for analysis? Really, you want to do this if you have a SIM, your preferred SIM vendor should be able to help with this. But I'm going to go through kind of a built-in function many people don't know about. It's easy to use Windows Event Forwarding through GPO to configure the forwarding of PowerShell logs from the workstations to a central collector. At the central collector, you can install an agent like nxlog and say, hey, send all of these events from the forwarded event store to a syslog server, to a database, really to anything you want. So it's kind of just one way for analysis, but if you have a SIM, most likely they should be able to collect the script block logs and Windows security logs from the endpoints. Okay, so analyzing the PowerShell data. I spent so much time trying to create rules on detecting malicious PowerShell, and then just to realize that I don't think this is going to work. I sat in the corner and cried for a little bit, and I got up and I said, okay, let's figure out how we're going to do this. So I had two major findings from that. Many malicious samples were obfuscated, but when they were obfuscated, immediately after you've reviewed hundreds and hundreds of logs, they stick out like a sore thumb. No programmer in their right mind can execute or can code that, or if they do, they're messing with somebody. So I have yet to see a legitimate use of obfuscated code. If they were not obfuscated, they would frequently use strings that were known to be suspicious or malicious. So, basically, that's saying if I look at a suspicious event, almost immediately I can tell that this is doing some shady stuff. And I don't even program in PowerShell. I'm a threat analyst. I look at create use cases, things like that. So it's pretty straightforward to understand, at least in my opinion, after you've looked at some and studied this a little bit, what's bad and what's good. So we started identifying high-level features that seem to indicate, what's malicious code. If you can look at it and understand that it's malicious, why is that? So we started asking myself questions. Why is this malicious? And here's all the reasons why. So I'm gonna start going through that. The first one really is quantities of known suspicious and malicious modules. Immediately, when you look at something, you say this is taken from a real malware sample, deployed through a Word doc, and executed, and it has references to invoke shellcode, PowerSploit, Meterpreter, persistence, really you see anything, that's a red flag immediately. You know something's going on there. Hopefully it's a pen test, and if it's not, you got to start digging in there. And you see there's a high quantity of these in the events that's being executed. We noticed, too, that there was a lot of kind of evasion tactics, like strange capitalization. It appeared that the code would be randomly uppercase or lowercase. Most code is not gonna do that. So how would you identify that? Well, I would imagine that most of your code is kind of at a known ratio of uppercase to lowercase based on the first letters and things like that. And these, when you have 2 times the uppercase or equal amount uppercase to lowercase, that's pretty significant. And then obfuscation and coding. This really entails any custom way an adversary might try to hide your code. So they can slice it, dice it, rearrange it, replace it, put it back together, compress it, execute or encode it, anything. So there's a great framework called invoke obfuscation that basically can take your nice PS version table, make that 10-letter command into a 1,000-word command line argument that's illegible to any human and encoded in multiple different ways. But yeah, it can still be executed. And what this does is obscure the code from automated analysis. Logs are going in your sim, you're looking for code, and you're looking for specific strings like, I'm going to look for an interpreter, invoke shellcode, or maybe you got an awesome list. But this is going to bypass that. And then we saw in a lot of samples from malware, it would be a high ratio of special characters. You look at this, and I don't think that this is known PowerShell to anybody. I hope not. This just looks ridiculous. And why does it look ridiculous? It just has so many special characters. So we figured that would be a good one to look at. And then finally was the cosine similarity. There's a great blog post we'll reference here from Lee Holmes where cosine similarity basically says, does this event, how similar is it to known good events? If we have a list of known good labeled data, we can take that event and say, score it based on how similar it is to those. So from there, here's an example of just taking 2 events and scoring it. You see that the top one is an event from a good log source, and a good log source that scores pretty high. The cosine similarity of a good log source to a malicious log source, very low. And what we do is we take our set of labeled known good and compare it to the known bad that we're examining at that moment. And so just knowing that, it's pretty easy to implement in Python or R. So that's just a function you can use to derive your features. So we've outlined kind of a lot of high-level features. These are things that our analysts are looking at and saying these are what they're using to judge the how suspicious that event is. So now we're going to kind of go into why machine learning and how to classify this and train a model. So as I learned, there's a never-ending cycle of creating rules and detecting bad behavior, and then detecting the bypasses, and then detecting the bypass can go on forever. So we have a better way. With those features, we kind of so we had identified the high-level features. Those would be tougher to bypass than just string matching and things like that. And honestly, I, as a data enthusiast, wanted to work on a problem that wasn't classifying flowers, right? So I'd gone through some classes, and you see the same stuff on the internet, and I'm like, okay, this is directly applied to me, and I think that we can do this. So it was a lot more fun. My machine learning really comes from self-taught. I'm not a programmer. I'm not a data engineer or machine learning expert. I've studied Coursera courses for the last probably 3 or 4 years and just kind of tried to learn because I think it's a tool that any data analyst, threat analyst should pick up because this is, I think, where it's going. Adversaries are making their behavior fit in with normal activity, and that's getting tougher and tougher to identify. Everything I did really was in R, but I built this in scikit-learn just because it transfers to my team. A lot of people work with Python better. I was the only one that kind of wanted to work with things in R. Scikit-learn is great documentation. So, I had learned the frameworks in R using the carrot package. Looking at this, I was able to do this pretty quickly. The raw events came from both Windows security logs and the Windows script block log. So we had samples from people who are friendly and said, hey, Derek, I'm interested in what you're doing. Here's a whole ton of data. We even generated some malicious samples for you. Here you go. So we took those, collected them. And really, we need to make it into a form suitable for learning. So if you look at this is really free text, right? So free text, in this case, isn't going to work too well in our learning algorithm. So we need to transform it into a form that would be. So me and my partner locked ourselves in a room for probably months on end, classifying, I think we had like initially pretty thousands and thousands of known good and known bad events, also generated adversary samples, also collected from our phishing campaigns, things like that. Really just begged, borrowed, and stealed as many samples as we could. Well, we didn't steal anything. It was all legit, so I have to say that. So for each event, we created a vector of value. So first was a ratio of uppercase to lowercase, like I mentioned, special characters to total characters, alpha characters to total characters, the cosine similarity, the count of suspicious modules, count of malicious modules. Now keep in mind, this is what we used at first. This is not what we use now, and we'll go into the details first. But this did work pretty well. So here's what we did. Here's a sample event. This has been some command obfuscated with invoke obfuscation. We create functions to derive each one of those values. Those are the values there. And basically, it's just it's a CSV file full of labeled data. Yes?
Out of curiosity, were you using, for the raw data, was that their traditional Microsoft event log format or the newer XML format?
So the events that we got so when we store the events, they're stored in raw text. So we collect them, and I guess they're not stored in XML. So we've collected them through the process, kind of similar to what I showed earlier. You have the log sources, NX collected at central location, NXLog sends them, so NXLog transmits it in text. So it's not an XML or any other format. So it's just open text that we process. And essentially, we extract the last field that says process command line. It's formatted almost exactly the same, too, with the formatting characters. So here's just an example of how we derive the values and what each record looks like. It's just a CSV file when you think about it. And it ends up looking like this. And if you're familiar with machine learning and you see a file like this, you're like, okay, this is kind of all the hard part has really been done at this point. There's some issues with this data, but it's there and it's usable. So it's time to start evaluating algorithms. So there's so many, when I look at scikit-learn, there's so many algorithms. I'm not a data scientist, so I'm not sure which ones will work the best. So what I found was that I'll just try all of the ones in there. So I found some good sources for kind of creating a test harness to iterate through each one, develop the accuracy, and we'll kind of go through that. But these were the initial ones. We had more like an MLP classifier. So we ended up looking at other ones in addition to these, but they all performed very similarly. We use k-fold validation. So we took our test set that includes known good, known bad samples. We divided that up into like 80-20. With that 80% data, that's our test set. The 20% was kind of our validation set. And with that test set, that's what we use to train the algorithms. And this is kind of the process of how we trained. We use k-fold validation, which what that does is say, hey, we're going to split the data up k times. So in this case, 5. And we're going to iterate through that and train it on 4 pieces of data and test the accuracy or test the metrics on the 5th piece of data. And then we're going to iterate through each piece. So all the data has been trained and all the data has been tested. We did 10-fold, 10 splits, but in this example it's 5. But either way, it worked pretty well. So initially we did scoring with accuracy. Our accuracy was off the charts, and I'm like, okay, 99.7%, I'm done. Here you go, guys. And really that was pretty good, but there's issues with this. So here's the distributions of the different algorithms and how they worked out. See the random forest, linear regression, KNN, and CART worked pretty well. There were some of the other ones that did not work very well, and I'm going to talk about why those didn't work well at the end. You may be seeing this already. But anyways, I saw that there's 4 that worked approximately the same. Each time I ran through that, it would change slightly. And that's one thing to keep in mind with machine learning algorithms. It wouldn't be the same results every single time. You would get slightly different accuracies and metrics each time you run through the process. Okay, accuracy is 99.7%. But in my data set, it's highly imbalanced. And we'll talk about that issue later. But so even if I were to guess benign every single time, I would have like a 93% accuracy, which sounds good. In reality, that's the worst that I could possibly do. So we need to look at other metrics like fault or precision and recall. So these 2 metrics kind of are what we're interested in, because we're interested in a good ratio of catching everything, but not sending false positives to our SOC too often. So precision, what percentage of suspicious classifications are truly suspicious? So if I guess there's 100 malicious samples, then what percentage of those are actually malicious? Recall is a little bit different. So what percentage of truly suspicious events were classified as suspicious? So let's say there's 150 truly suspicious. What percentage of those are actually were classified as such? So it's a slight difference. It took my head to a while to wrap around it. But Wikipedia, this is like the classic picture of how to understand precision and recall. I suggest taking a look at it. Anyway, we use we end up using the F1 score, but here's the precision. So the precision for random forest is pretty high, 98%. So what percentage did we classify? Our classifications were truly suspicious, 98%. Our recall, what percentage of our truly suspicious events were classified as suspicious? 96%. So that was pretty good. And then we end up using our F1 metric, so 97% on random forest. And we're pretty happy with this. This is significantly better than our rule-based approach that's triggering thousands of false positives to our SOC and missing some known things that we thought it should be catching, and we end up catching through other means, detections through other products, et cetera. So what we're interested in is kind of a good balance. We can't send too many false positives to SOC. We want to catch everything. And so how you show that's through the ROC curve. That was, I think this is obligatory for any machine learning model. This ROC curve looks ridiculous. Keep in mind, it's based on one customer's worth of data when I created this. So, without a extremely varied set, you're going to get a really good looking ROC curve. But what this shows is that it's way better than luck. And so we're doing pretty well here. So we end up with the random forest algorithm. It was the most accurate, tested at the time. We ran that for a long time against all of our data. So the algorithm needs to be tested against previously unseen data. So we're training and testing on the same on our test set of data. Now I'm going to give that 20% that I set aside. We're going to run this model and say, hey, how does this do on previously unseen data? It's very important, if you're not familiar with machine learning, that you don't train on the data that you're validating on. That's like memorizing version 1 test and then giving version 2, and you're like, oh crap, none of this is the same. So we train the model and test the accuracy on the validation set extremely high. So you see that on this test we had 1,500, roughly 1,800 samples, 99.8% accuracy, and you see the F1 scores were really well there. So we think that this was really good. And at this point is when I showed this, I'm like, okay, this is where I'm trying to justify putting additional resources to get more data, to talk to more clients, to get the pipeline, to say, hey, we want to apply this to everybody. And so random forest had the highest accuracy. We used this for a while. It's very successful. So what I show is we reduced false positives significantly. Our SOC was looking at every instance of encoded commands. That's used quite often for legitimate uses. So they would have to decode the encoded command, take a look, and make a judgment call there. That's time consuming and a waste. It ends up being like 1% of the encoded commands were actually malicious. We increased our true positives. So things that were being missed before are not being missed now. So when we detect that malicious PowerShell actually caused this service to run, that service running is what triggered like a carbon black watch list rule. We think, wow, we should have saw this PowerShell event earlier. Why? But now we're seeing those. And we decreased false negatives. So we could do this we ran in parallel with our existing rules. So we could see the things that were missed by them and that we would never have known if it wasn't for this. And we also test on sandbox events. We get tons of phishing documents. And so they detonate them in a Cuckoo sandbox. We get the logs. We analyze those. If we see a PowerShell sample from a Cuckoo sandbox, most likely that should be malicious. And someone reviews every single one of those. So that kind of helps us say, hey, okay, this thing's working well. And that's it. No, I'm just kidding. So if you look through here, pitfalls and lessons learned. This is the gold, right? Like if I saw this is what I would be happy with. So that was the end of the POC. I'm definitely not at the end of the story. This was probably the middle of 2017 when this portion was done, or early 2017. So we learned a lot of lessons and we enhanced this model significantly. So I'm going to go through some of those enhancements, talk about some of the problems. Obviously, can't talk about the exact specifics of our pipeline that we're running, for our clients. But I think that with these lessons are what we derive that from. So it's really worth its weight in gold in ML. So one of the biggest questions I get. How do you account for overfitting? How do you, feature engineering? Our data was pretty good. We had a lot of malicious samples. We generated a lot of malicious samples. We were able to get them from sandbox events. We were able to get them from clients. And we took care to separate our test set and our validation set. But one of the issues is our hand engineered. You can see that these are really hand engineered predictors, right? So we created these. We decide what's suspicious. We decide what's malicious. It requires our judgment to do that. Also, each one of those malicious and suspicious samples are not as malicious as the others, right? So you have a suspicious events. You see invoke expression, often seen in malicious samples, but also seen in legitimate samples. At first, I thought, okay, these were always malicious. That's not the case at all. So how do we fix that? So we already played really good close to to separate our training and validation sets. What we did here was update our feature engineering to address this issue. We ended up drastically increasing our feature set, but I can't go too much into this. But basically, we stopped using the suspicious and malicious count list. It worked pretty well, but and better than our rule set, but it did not work as well as we needed it to. So that's about as far as I can go there. And if you think about it, if I'm creating a list of suspicious and malicious modules, that's from my experience reviewing these logs. And so even though I split the training and validation set, I've essentially looked at the validation set and generated this list of suspicious events from that set. And now I'm creating training the model on that. So really, that's kind of overfitting to that data. And we kind of learned that afterwards when we introduced more data, you start seeing things like common modules used at one client that are not used at the other. And you're like, oh, this is actually used. I can't believe that, like encode a command, invoke expression. So that should help if you're working on this. There's also some references at the end. The bad data. So I found that certain algorithms prefer normalized event data rather than the raw numbers. So if you saw, we had specific counts like 16, and then we would have the cosine similarity be 0.05. Those are not normalized or standardized in any way, and a lot of algorithms require that. So basically, when I was looking to research this, standardizing or normalizing those events are really good for any algorithm to work. So now everything's a number between 0 and 1. You take all those suspicious counts and you convert them into less numbers between 0 and 1, like I said. And this is probably the reason for the really poor performance in some of those algorithms that I was showing earlier in the distribution. We didn't go back because random forest worked really well still, even when on normalized data. So, and we can really we'd spend a lot of time increasing the accuracy for very little gain. So here in scikit-learn, you have the normalizer and standard scaler. You can look that up. Basically, we just apply that to the data set and then train and predict based on that data. Here's some links for that if you're interested. And I really just suggest looking at the scikit-learn, especially if you're new. It walks you through everything. And really make sure the data fits your algorithms. Like, I'm kind of blindly saying normalizing data is best. There may be some edge cases where that's not true. I'm not sure. But it's worked well for us. Probably the biggest one in any machine learning data science problem, not enough data, lack of diverse data. I'm in a decent position, not as good as Microsoft is, but we have quite a bit of data. So we're able to, each model makes the predictions based on what we've previously seen. So of course you want to see as much as possible. Not enough data and really need diverse data. So like I had a good quantity from one client. When we introduce to other clients, they do things differently. What's normal to them is not normal to others. So we're able to kind of differentiate that, learn those features, and apply that to everybody. And really, the way to do this, get more data. Beg, borrow, steal, or don't steal it. Generate additional data. Luckily with PowerShell, there's lots of ways to do this. Like I said, there's those PowerShell frameworks to do bad stuff that you don't need to know PowerShell that well. I'm pretty familiar with adversary techniques and tactics, so I'm able to kind of run this in a virtual environment, generate the data that we want, without much of an issue, but it's not that difficult. Also, if you get phishing samples, you can take a look at that. So also, even just looking at Twitter, we literally saw samples on Twitter, so that were pretty interesting. One other thing would be label, label, label. Make the labeling as easy as possible. When we had a system where it was difficult, I'm literally copying these features from one file into another and combining them. That sucks. If you have a system where you can review the event, see the prediction, and classify the event, that's great. And then use that for subsequent training. From the beginning, measure your performance. So I'm a security guy. I'm not a data science guy. I didn't measure hardly anything at first, probably nothing. I just saw, this classified most everything pretty well. Then I start getting questions asked like, what's the false negative rate? What's the false positive rate? Show me a confusion matrix. Show me a RAC curve. Show me all these things. And I started learning that as I went through. From the beginning, make sure you can measure that. And we're still working on that a little bit. Just have good measurements to say, okay, this is operating well. Because, one of the questions I get a lot is concept drift. What are we classifying now as malicious that we may not have classified back then? That's hard to understand, and we take a look at that through kind of QA type activities. When we see things that are being classified from a sandbox, we take a look at that. If it's classified as benign, and we need to understand why it was classified as benign. So it's easy to avoid collecting metrics. This is probably, if you take one thing away, your ability to describe the value of the model is as critical as the value of classifying the events. Because if you cannot describe the value of this to people that are going to give you time and resources, then it's never going to be implemented. This has to be done and has to be able to show that this will provide value. And I'll show you how I did that. So for our use case, precision recall far more important than accuracy. We had a highly imbalanced set. One thing I learned from this conference was that if I'd known about SMOTE back then for compensating for the imbalanced data set, that may have helped a little bit. We didn't really have that much issues though in terms of our precision recall being affected by this though. So I'm not sure how much of an imbalanced data set causes problems in this case. Measure everything from the start. Make sure the value is easy to convey. Oh, and this last one. Code names tend to stick around. So from the beginning, we did not know if this was ever going to work. It was kind of a pie-in-the-sky activity. My partner said, hey, let's call it Project Blue Steel. It sounds cool. It's from one of the best movies known, probably next to Casablanca. So if you haven't seen it, go check it out. You'll be overwhelmed, I'm sure. So obscure references are obscure. Not everyone has seen Zoolander. So I learned this one the hard way because blue steel just kind of sounds cool if you've never seen about it, right? It's like steel, it's blue, but no. It stuck around though, and you may see it if you take a look out there. But so here's how I communicated the results. We took a look at our detection efficacy. We had an increase in 28% true positive rate. So we're catching more stuff with this. Our false positive reduction was decreased by 99%. And that's because we're not investigating every single instance of encoded command and every single instance of invoke expression. And we see that a lot, especially where people are orchestrating updates and things like that. That alone showed and said, hey, this reduces time, saves money, reduces analyst load, which time is money, right, in the case of a SOC. And so we're like, okay, let's move on this. So that was kind of the end of the POC. At that point, we moved on it. We went to productionize it. We implemented collecting metrics. At first, like on my POC, it was a batch processing. Right? I'm just classifying a whole batch of events. We're not doing this in real time. Now we've got a real-time pipeline. We're taking a look at a large scale, pretty much all of our clients' data and pushing it through this. So we've got so much value from what ends up to me, I think, being far less work than creating rules, constantly updating those rules, constantly whitelisting those rules, constantly creating new ones, trying to bypass rules, things like that. So we were quickly able to iterate and generate a robust model. It was easily updated, so we updated with new samples constantly. We had a training, a way to train the data efficiently, and we constantly monitor it for false positives and false negatives, right? So we obviously take a look at any false positives that come, or all the malicious samples, anything classified as malicious is being looked at. Anything that's being generated from a sandbox that's classified as benign is being looked at. So, it's impossible to say I'm looking at all false negatives. Obviously, it's one of the hardest things you can do, but we're doing a pretty good job there. And with this, we're raising the bar significantly for our detection. So it's far more difficult to evade this than change the capitalization on your script to bypass some case-sensitive rule that's in place. And improved analyst efficiency. So that's really what this was all about. And so that's about it. There's emerging work in this area. So detecting malicious PowerShell commands using deep neural networks was a reference paper recently released, or an academic paper recently released. I'm not sure if that was the one that Ram had referenced, but it looked like it could have been. Revoke obfuscation is one where they're using kind of machine learning techniques to detect obfuscated code. And then also FireEye recently released a blog post that was similar detection mechanisms. So if you're interested in this subject, take a look at those. They all do, every one of us do things a little bit differently. Every one of us has had pretty good results, and we've operationalized this for really 2 years. And we've caught nation-state attackers, pen testers, really highly advanced threats across many locations. So probably the best work I've personally implemented. So here's more resources, right? So I have the data set in Jupyter Notebook online if you want to go through and kind of just be kind to, like I said, I'm not a programmer or a data scientist, but that's kind of a walkthrough that you could take a look at and do yourself. The data set does not include PowerShell code because I can't show that. It's usually specific to the organization. You might even have passwords or usernames in that in some cases. We do our best to remove that. Invoke obfuscation, revoke obfuscation from Daniel Bohannon. I apologize if I got that incorrect. Really, that's how to generate adversarial samples and how to detect obfuscated samples. If you want to take, Palo Alto has a ton of encoded commands, thousands and thousands and thousands. So if you want to take a look at some samples, let's see, the Lee Holmes has a blog post on Cosine Similarity. That's kind of what got me down this road when you see this, because that was hard to using that. Cosine Similarity detects obfuscated code very well. And then machine learning mastery, process for working through machine learning problems. A very wise man showed me this process. Here's how you could go through from training, testing, showing metrics, things like that. And this is a good way to do it. So that's about it. Do we have any questions?
The things you were classifying, were they an overall PowerShell script?
The things you were classifying, were they an overall PowerShell script? Was it a line of code? Was it an individual execution within a line?
So there were either two things. They would be from the command line, just the command line process. So it'd be the binary and then all the arguments that you provided. Also, so that's just one of them. So it's an event, and we're pulling one field from that event, the very bottom one. Second one would be the script block log. So if you were to execute, like, let's say PowerShell.exe do bad stuff.ps1, that you wouldn't be able to tell if that's malicious through classification. But the code that's executed from that is stored in the logs. And they divide those up. There's like a limit, like a 1,000-character limit, and they'll divide those up. We take a look at those as well. So
I'm not trying to be an asshole, and I don't come from the blue team.
yeah.
Thank you. I'm not going to say the first two lines that I said. But I get that admins need to execute PowerShell to do their job. But what if they're doing in a window, and if you notice PowerShell being executed outside that window, then you just raise an alert?
Well, that would absolutely be the best, right? Like if you would have, that's kind of like a whitelisting approach. And if you're in a mature organization, that would work very well. But I find many organizations have a hard time even logging PowerShell. So to implement a policy like that would be extremely difficult and unreasonable in many places. So yeah, absolutely, I would say that. Or you could even create a whitelist of people who can execute. Like normal users may not execute PowerShell, right?
Exactly.
So things like that. So you could potentially do that, a whitelisting approach, but I find that to be difficult. And in reality, it isn't implemented that well. If you can do that, do it absolutely. So. Any other questions?
As far as detecting these malicious PowerShell scripts, is there anything that you've been working towards to make the case for preventing them so that in real time that it would be stopped before the damage was done?
So things like that are done. That's kind of out of my realm of concern. I'm a threat analytics. I develop threat analytics, right? So we have, really in reality, if you can do preventative measures like least privilege type stuff, we have advisory services that say, hey, here's what you guys should do. Do good passwords. Don't get exploited to begin with, so they can execute PowerShell. I don't look too much. People have talked about signed PowerShell, things like that. I think that would help. But I'm just only thing I really like to do is detect bad stuff. So unfortunately, not a ton. But I'd be interested in what other people are doing there.
We have only time for one more question. Any last questions?
Hi. So you got data from the command line and also from script block. And for the scripts, it can be very long, right? So do you see any difference or whether it affects when you try to get the features? Or does the ratio looks different from the data from script block versus from the command line?
So not really. I haven't noticed that. Not to say that there aren't any. I hope that if they are, that they're being learned in the process, because we have, if it's intermixed. Also, anything you see in the command line is typically included in the script block log as well. So if you saw PowerShell exe with the encoded command, you'd still see that in the script block as a separate event as well. So that would be included, even if you're just looking at the encoded command. So, definitely the scripts are longer, right? You got huge backup jobs that are very long. But those would also be broken up. So how you whether you reassemble the script blocks or analyze them in blocks, kind of getting into too much how we're actually productionize this, and I don't want to get too far, but you could reassemble the script blocks, or you could look at just the script blocks. Because one of the attacks you see is, okay, we'll mix lots and lots of known good code to sway these types of heuristics. But if you don't reassemble them, then maybe there's a block that contains that. Potentially, you could spread the code throughout the whole thing. What I notice is attackers don't do that yet. So it doesn't really answer the question, but I haven't observed that myself. Yep, thank you.